You weren't able to find any problems that...
Well, I just haven't had time. I mean, we worked till 6 yesterday, and then I had a calculus session late last night. So I haven't had time to do it. And yeah, I might be able to find some, though. I just wanted to, in general, talk about sequences. These are the kind of sequences you're liable to be dealing with. You also mentioned inequalities.
Yeah.
In what sense are you having trouble with inequalities? Solving any equation? Like,
they're just the type of problems that always give me issues. That's why I kind of wanted to focus in on those. Because talking about them...
You can solve this, right?
Well, yeah, I moved the 3x.
Yeah, you solve it exactly like you would solve an equation. There's only one difference in inequalities compared to equations, and that's when you have to divide by a negative number, you have to switch the sign. Okay, so let's do that here. Let's move the x on the right to the left, making minus 4x. Let's move the 1 on the left to the right, making 1. Now what?
So you moved the x to the left, got negative 4x, moved the 1 to the right. Now if you divide by negative 4, you have to flip it and say it's x less than or equal to negative 1 over 4.
Right. So if you know how to do that, I don't know what else to tell you about inequalities until once again we encounter a problem and we can talk more about it. That's about all I think you need to know. Now, if you have, I noticed that we had one problem where we had something like this, and you weren't sure which side to shade. This has a y-intercept of negative 3. It has a positive slope. So what part of this graph fits this condition?
I'd say the bottom right half.
Yeah. In other words, that part there. And the only thing I look to is the y component. Its y is less than this line. So I go to this spot right there, and I know it has to be in this direction because that's where y is less.
What if it was y is greater than negative 3? It'd be the other side?
Uh-huh. Yeah, if it was that, then it would be this side over here. Okay. Probabilities. Kind of probabilities you're going to encounter. That one with the bad apple is a really good one because that's an example of a complement probability where you don't figure out the probability of the event, you figure out the probability of the rest of what can happen and you subtract it from 1. And it's easier to do that because it was far easier to figure out the probability of getting 2 good apples in a row than it was the probability of getting at least 1 bad apple.
All right. Yeah, it's better to go over problems. This doesn't help me all that much.
All right.
Just go through.
169. So how are you doing it?
I got C.
Okay. Did you write out the numbers full? In other words, did you do it like this?
I did. No, I did 100 million. I just checked how many places there are on 100 million, which is, so after the 100, there's 6 more places. And so in any 1 billion, no, I didn't do that.
You didn't do it that way?
No.
Uh,
I just took 100 million and said in every 1 billion, there's 10. There's 10 100 millions.
mm-hmm.
And so I multiplied 96 times 10, and then multiplied that by 3.
Okay. If we did it this way, we could just cross off all the zeros. In other words, we have 8 zeros there, which means we can cross off 8 zeros there, and we have a 30-to-1 ratio. So we just multiply that number by 30, and we get that.
Okay, so you did 3 billion vehicles traveled, and 100 divided by 100 million, pretty much what you did.
Right, I'm looking for the ratio. In other words, what's the ratio of 3 billion to 100 million? And I'm going to take that ratio and multiply it by 96.
Okay.
Now, perhaps an easier way would be to use scientific notation. In other words, I could write 3 times 10 to the 9th divided by 1 times 10 to the 8th gives you 3 times 10. There's our 30-to-1 ratio. But if you're not real comfortable with scientific notation, that might actually be a slower way to go. I would say this is probably the most accurate. This is the way I would do it if I was taking the test, I think.
Okay.
All right. Can you see that? Can you read that, or do I need to blow it up just a little?
No, that's fine.
Okay.
Okay, so 70% have not passed the test. So 30% pass, 70% not. Among the members who have not passed the test, 12 have taken the preparatory schools and 30 have not.
This has a signature on it, which is a very simple final question that immediately tells me this should be a back solve. When I see how many members are there in the swim club and there's nice round numbers, I'm going to back solve. You see that connection?
Yeah, I got it. Okay.
Now, it depends on how complicated that question is, but the shorter it is, the shorter the sentence, the more likely it is to be a back solve, because they're not asking about a difference or a product or anything like that. It's a straight, how many members are there in the swim club?
Okay, so if we assume 80,
Okay.
well, 30% of 80, 8 times 3 is 24. So there's 24 who've passed, and there's 36, no, 56 that have not passed. 12 have taken the preparatory course and 30 have not. So that doesn't work.
Okay.
We need to go bigger. So let me go to 100.
Hold on just a second. We ended up getting 42.
Right.
Right? And it needs to add to 56. Okay. So we don't want to do 100 next. We want to do 120 because 120 will definitively tell us the answer.
Okay.
If we did 100 next, that might not. We might still be wrestling between D and E. But if you do D next, you'll positively know.
Okay. So 120, 30% of 120 is 12. 12 times 3 is 36. So 36 passed. 84 have not. Which means that 12 have taken the preparatory. 12 have, among the members who have not passed, 12 have taken the preparatory course and 30 have not. So that's 42. It doesn't add up either.
Which tells us what? Not only does it not the correct answer, but it tells us we went the wrong direction.
Oh, we were supposed to go down.
That's okay. We just figured it out and we know the answer. In other words, we still figured out the answer with just 2 tests without, even though we didn't know which direction to go. And that happens sometimes. That's why back solving is so beautiful. Because when you know which direction to go, you take at most 2. And even when you don't know which direction to go, you can kind of tell you went in the wrong direction.
Okay. So
okay. Just to prove it, let's do 60.
All right, 60. And 30% of that.
It's 18. 42. 12 plus 30 is 42.
Yep. Okay. I should have been able to tell that I needed to go down. That's a good, that's all right.
I wasn't 100% sure myself, but what I was sure of is that if we were going in the wrong direction, we would find out that we went in the wrong direction, which means we would have our answer. In other words, it didn't matter whether we were going in the right direction or not. Either way, we would determine our correct answer.
Okay.
Okay, 171. Okay, good. Here's a sequence. Now, this is not an arithmetic sequence. It's not a geometric sequence. In other words, there's not, the difference between those two is 2. The difference between those two is 3. It's not arithmetic. It's also not geometric because 4 divided by 2 is not the same as 7 divided by 4. So this is some other kind of sequence, which is fine. We just have to figure out what the 6th and the 5th terms are. We've got the first 3 terms. Notice how they got the first term. N was equal to what?
The first term is 2.
No. Right, but N was equal to what? In other words, when you talk about sequences and you talk about the nth term, every term in the sequence, that's the first term, so N is 1. This is the second term, so N is 2. Notice that when N is 1, I get 1 plus 2 to the 0th power, which is 1 plus 1, which is 2, the first term. The second term, N is 2. So we have 2 plus 2 to the 1 power, that's 4. Notice what we're doing. So let's figure out the 4th, 5th, and sixth terms. So when n is 4, what is the fourth term?
One second here.
You don't even need to do n is 4. Let's forget n is 4. It's not pertinent to the question now that I think about it. So all we need is the fifth and the sixth term. In other words, n is 1 here, n is 2 there, it's 3 there, it's 4 here, but we don't need that term. What we need is the fifth term and the sixth term.
So you have 21.
So n is 5. What do we have?
And
So when n is 5, what is the term?
21.
It's 5 plus 2 to the fourth, 21. Okay. So that's 21. What's the sixth term?
6 plus 2 to the fifth is 16 times 2. 32. 6 and 32.
2 to the fifth, yeah, 2 to the fifth is 32. It's a good idea to have those memorized for the GMAT. Being able to count by twos. 2, 4, 8, 16, 32, 64, 128. Those are all the powers of 2. And they ask a lot of questions regarding powers of 2. So it's not bad to have that one memorized as 32. I know that 2 to the 10th is approximately 1,000. That's, if you keep doubling that, when you get up near 1,000, that's 2 to the 10th. So the difference between the fifth and sixth terms?
17.
Right. And notice it would have been a waste of time to figure out the fourth term. We didn't need it. I don't know what it is. I don't care what it is.
So one more time, when they're speaking about the nth term, they're not asking me for the value of the number.
Sequences are defined as n being integers, and it can start at anywhere from 0 to 1. In other words, you have n going from 1, in this case, up to 6, and the nth term was like that. So in other words, the first term of the sequence is when n is equal to 1. The second term is when n is equal to 2. And actually, this is a series, and they're really talking about sequences, so we don't need that summation sign. But sequences are where n takes on only positive integer values or 0 and counts up towards some number, maybe infinity even. In other words, if I had a sequence that was the nth term is n factorial, tell me what that sequence is.
N factorial is just n.
What's the first term?
N.
The first term would be 1 factorial. The second term would be 2 factorial.
Why?
Well, because when you have a sequence that's defined by the nth term, the way that works is the first term is when n takes a value of 1, the second term is when n takes a value of 2, and so forth and so on. If I said what was the sequence between 2 to the n over n factorial, this is a sequence. The nth term is defined as that. Well, what's the first term?
2 to the 1 over 1 factorial.
Right. What's the second term?
2 to the 2 over 2 factorial times 1 factorial.
Well, just 2 factorial is 2 times 1, yeah. the third term would be 8 over 6, and so forth and so on. That's the way sequences work.
Why would you put 6 instead of 3 factorial?
Because it's 3 factorial. 3 factorial is 3 times 2 times 1, which is 6.
Okay.
Yeah, I should have written it, I guess, like this, 3 factorial. But eventually you turn those into numbers.
Okay.
So that's how the nth term of sequences work. So good. I'm glad we had that problem.
Now we're on
172.
I'm going to rewrite it.
Okay. Into what?
Just going to foil it and see what it looks like.
Okay, that's going to probably, here, let's do it real quick, but you'll see that that's going to take you away from where you're trying to go, not closer. What's another way to solve that equation?
So yeah, I got
How do you solve equations where one side is squared?
square the other side.
Take the square root of both sides.
Yeah, take the square root of it.
Okay, so notice if I take the square root of the left side, I'm left with that. What's the square root of 400?
20.
Okay, it's actually plus or minus 20. And that's an important thing to remember. It may not be a factor here, but it might be. So I actually have two solutions for x. What are they?
So if you say plus 1, you have x equals plus or minus 21.
Well, let's take the plus side. So if I add 1 to that, it would be 21 as one solution. And the other would be, if it's minus 20, then it goes to minus 19. So those are the two solutions.
Okay.
Now, x minus 5 would have to be what?
X minus 5. It would either have to be negative 24 or 16.
And 16 isn't on there. So, in other words, the only way you were getting this problem correct is if you remembered this plus or minus right there.
That's the only way.
I think so, because it's not one that can be easily back-solved. That's not really true if I think about it. If I try back-solving this, and if x minus 5 is equal to 15, that means x would have to be 20, and 20 minus 1 squared does not equal 400. So that answer is wrong. And I would end up continuing on, and when I found this, I would realize that that works. So I actually could back solve it, but it's a little tricky. This is not a classic back solving because it's asking you for a difference. So you can't just start off with the number and go back and plug it in. However, it's not that hard to make the leap from if x minus 5 is 15, then x is 20. Right? So it really could be back solved.
Yeah.
And back solving would eliminate the need to put this plus or minus in, which everybody forgets. They really do. I would say 75% of my math students forget to put this plus or minus in when they're taking the square root of both sides.
Yeah, I'm going to write that down like here in my notes.
Okay. But notice how foiling that out was going in the wrong direction. If it had been foiled out to begin with, we would have wanted to factor it into an x minus 1 squared because it makes this easier to solve. I guess after foiling it, you could have turned it into a quadratic and factored it.
Yeah, I got the quadratic was x squared minus 2x minus 399.
Yeah, that would have been a hard quadratic to factor is the problem.
Yeah.
So it's far easier to take the square root of 400 than trying to factor 300.
With the numbers that we picked, x being 21 and negative 19, yeah, it works in that quadratic. But there's no way I would have found those two solutions.
Yeah.
With the quadratic, you know.
Right. Right.
All right. So let's see the next one.
Okay. Good. This is an inequality, and it's an inequality with a tricky part to it. So I'm glad we came upon this.
All right. Well, I'm just gonna try to solve it.
Okay. Solve it algebraically.
Sure. And then there's a negative x greater than or equal to negative 1. So I'm gonna move.
Hold on. Hold on. Let's get to this part first. Okay. Now, we can divide both sides by negative 1 as long as we switch the sign.
Yep.
Right?
Yep.
Now, here's the tricky part. That means x is less than or equal to plus or minus 1, and you have to switch the sign.
Huh.
When you take the square root of both sides of an inequality. And I'm trying to remember here. Let's see. If x squared is less than or equal to 1, then x has to be less than 1, or x has to be greater than or equal to negative 1. In other words, on a number line, any values that were in between those two values, this would be true. Right? When you square a number that's less than 1, it gets smaller. So it stays less than or equal to 1. So it's this range of values that we know to be correct. Well, let's just find the answer, and it's E.
Oh, you see how they put that or in there? And answer E? That's a little tricky.
It is. Well, plus, though, look at what that says on the number line. That's this part of the number line and this part of the number line.
X is less than negative 1 or greater than 1. Uh-huh.
In other words, they need the or in order to define two different segments that are not continuous.
So when we took the square root, how did we know which? We know that it always will. When we square root an inequality like that, and we're looking for an answer, is it gonna always be continuous?
In other words, I can make the following statement: if that's less than or equal to C, then x is less than or equal to C, or x is greater than or equal to minus C. Is the way that works.
That's always going to be true. So it'll be a range of number line that are connected or continuous. Make it E correct.
Yeah, because taking the square root of both sides is a little like dividing by a negative number, because this thing could be negative. In other words, x can be negative. But I'm glad that problem came up, because I forgot about that. What you do when you take the square roots of an inequality. Notice that we also could have back solved this. Could we not have? We can certainly eliminate A. If x is greater than 1, then 1 minus x is not greater than 0. We can eliminate b for the same reason. C actually works.
I don't see your logic with the if we move the -1 over.
Are you talking about back solving?
Yeah, I don't see how you.
All right. Here, let me get to a new page here. You see how we can eliminate a?
No.
Well, 1 minus some number that's greater than 1. If x is greater than 1, then this has to be greater than 1 also after we square it. That's a negative number. It's not.
Why does x have to be greater than 1?
I'm saying if we try to back solve it and we start with a, we can disprove a. If x is 2, 1 minus 4 is not greater than or equal to 0. So a can't be true.
X is saying x is equal to greater than 1. If you put that in the squared, you for example, you put 2 or 1.1, you get a negative value, and that's not greater than 0.
Right, right. Same thing for b, because a negative, a number less than -1 is like -2, -1.1. Same thing as when you square it, it turns positive and gets bigger, which is going to make 1 minus that number still negative.
Yep.
Now, C happens to work, and C is true, but you got to go back to the question, which of the following describes all values of x? Yep. And C is true, but it only covers half of them. It only goes from 0 to 1. It doesn't describe from -1 to 0 also.
Right.
So this is a bit tricky. This is one of the few questions you'll see on the GMAT where they actually give you two answers that are technically correct, but this one does not describe all values of x, but it does fit that equation.
Yeah, that's a good
so back solving could be dangerous on this problem, because back solving you're going to get to C and realize that C works and you're going to go with it. So here's a case where back solving is probably not the way to go, because most people that back solve are going to get it wrong. They're going to run into C and choose that.
Okay.
But if you didn't know how to solve that or handle the square root of each side problem, you can certainly do it the way I started, the way I did it basically. 177. Blow that up a little bit more. Probability. We're covering all the subjects you wanted to cover accidentally.
Yeah. That's good. Okay, 174.
Perfect. It's not only a probability problem, but it's the exact concept that I've been talking about.
So there's 3 tosses, and you want the probability that at least one of them will be tails. So according to what you were teaching before, let's do the probability that they will be heads.
All 3 will be heads.
Okay, so the probability each time is 1/2, 1/2, and 1/2. So I guess
what's the probability of 3 heads?
I'm going to say it's
You multiply, because they all have to occur.
1/8.
Okay. And all other situations have at least one tail. The only two categories are 3 heads and at least 1 tail. Maybe 2 tails, maybe 3 tails, but at least 1 tail, and that's what they're asking. What is the probability that at least one of the tosses will turn up tails?
Jeez. So it's just 1 minus 1/8, 7/8?
Yeah, 7/8. And that is the easy way to do that problem. The hard way to actually go through the combinations and permutations for one of them turning up tails is much harder. In fact, I'm not sure I know how to do it.
Okay.
But I know how to do this technique. And this is kind of what they focus on. And these kind of problems, complementary probability problems.
Probability is 1/2 that a certain coin will turn up heads on any given toss. If the coin is tossed 3 times, we go back to that one. I wanted to recap. Oh.
Yeah, can you see it now?
Yeah. If the coin is to be tossed 3 times, what is the probability that on at least one of the tosses the coin will turn up tails? So at least one, but it could also turn up all 3 times. We don't know.
Right. Had they said, what is the probability that you'll get exactly 1 tail? Now we can't do the problem the way that we did it.
So what would we have to do?
Well, I don't know. You could get a tail on the first toss. I'm thinking about that. If they said if it turned up exactly tails, well, that means that either you had.
Well, that means you have to write out all the possibilities.
Well, I can do that because exactly tails would be tails, heads, heads, tails, heads, tails. No, excuse me. It's not that hard to write them all out, actually.
There's only 4 combinations.
I think there's only 3. These 3 here. That's the only 3 combinations where you get exactly 1 tail.
Oh, exactly one. I put in 2 tails.
Okay. So since this is an or this, we figure out the probability of this specific combination coming up. That's 1/8. This is 1/8. And this is 1/8. And if you have or, you add these. So it would be 3/8.
You fairly confident about that? Okay.
What's that?
Are you fairly confident about that method right there?
And the only thing about that method that bothers me is if we flipped it 9 times. Yeah, I am. I do think that's correct, yeah.
So you flipped it 9 times. Is it possible that you could have?
Well, each of these is not going to be an 8th. If you flip it 9 times, each of those is going to be 2 to the 9th. It's going to be 5/12.
Why wouldn't it be an 8th anymore?
Well, because if you flip the coin 9 times, you have a 1/2 of getting a tails on each one. So you'd have these combinations, tails, heads, 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 and you'd have more combinations, and the probability of each one would be 1/2 to the 9th, and you'd add those up, but there'd only be 9 of them, and they'd still be less than 1. My hesitation as to this answer was whether sometimes it can be a little tricky on the ors, and you add them up, and you can see, well, I could get a situation where I get a probability greater than 1. And if ever that happens, you know you're doing it wrong, because you can never get a probability greater than 1. Here's a good example. I'm going to give you right now. If the probability that it rains on a given day is 60%, and on a second day it's also 60%, what is the probability that it will rain either day? You cannot add 60%. In other words, I'm saying what's the probability that it'll rain on day 1 or rain on day 2? And if I add these two percentages, I get 120%. Well, that can't be right. So I'm doing something wrong. My logic isn't. I can't use the OR principle to add those probabilities. However, what I can do is figure out, well, the only way that it doesn't rain on one of those 2 days is if the 40% probabilities both happen. In other words, if the probability that it rains is 60, the probability that it doesn't rain is 40, it would have to not rain 2 days in a row. That's a 16% probability, which means the probability that it would rain on one day or the other would be 84%. So you can't always add when it says OR.
Okay.
And
the probability of it raining on day 1 is 60. Probability of it raining on day 2 is 60.
So the question is, what's the probability that it rains on day 1 or 2?
Okay, day 1 or 2.
Now, most probability books teach you that when you see the word "and," you multiply the probabilities, and when you see the word "or," you add the probabilities. But here's a case where you cannot do that. You cannot add the probabilities because we said "or."
Right, so in this case, you want to do the complementary method.
Right.
So the probability that it won't rain on either day is 40% on the first, and on the second is 40 again. And in that case,
you multiply those together because both of them have to happen. In other words, it has to not rain on the first day and it has to not rain on the second day.
For it not to rain at all.
Right. So you multiply because we're using the word "and." So 40% times 40% is 16%.
16 minus 1. Okay. All right.
1 minus 16 gives you 84%, which is the rest of the universe. In other words, 84% actually covers it raining on day 1 or raining on day 2 or raining on both days. That's 84%.
Okay. Okay. And 75?
Yeah. Hold on, I got it covered up slightly. Okay. What does that last sentence and those answers tell you?
Back solve.
Absolutely.
That's
In other words, we're looking for a very simple question as that final question. They didn't ask for the difference between the students in sophomore and junior year or anything complicated. It's a very simple question that you can immediately fill in to all of the premise of the STEM.
Okay. So 110, remaining 10 grades, I'm going to subtract 10 first and get to 100.
I wouldn't do that. No, because you have to take 1/5 of 110.
Okay.
You can't subtract 10 and take 1/5 of 100. That's not what it says. 1/5 of all of the students have A's.
Okay.
So how many A's?
1/5 is 20%. So 11, 22.
Yeah, and the way to do that is to take 1/5 of 100, because you know that's 20, and then take 1/5 of 10, which you know is 2.
Oh, that's even easier.
Okay. 22 A's.
Okay. 1/4 are B's.
What does that tell us immediately?
25, but I can't take 1/4 of a 10.
It tells us that 1/10 is not the answer.
Oh, really?
Right. Because you can't have 1/4 of 1/10. There cannot be precisely 1/4 B's. So this was clearly a back-solving problem that if we'd have worked through it, we probably would have known which direction to go. But immediately we've come upon, okay, we can eliminate this one entirely. So rather than, let's go back and deal with these other 4 numbers that we can take 1/4 of. And in fact, we have to be able to take 1/5, 1/4, and 1/2. We can do that with 80. We can do it with 160. We can do it with 200. We can do it with 400. So I would say let's try 80 next. Let's stop the 110 without knowing which direction we have to go because we didn't spend a lot of time on that. So let's try 80.
1/4 of 1 of 80.
What's 1/5 of 80? First of all, how many A's?
16.
How many B's?
20.
How many C's?
20. And then half of 40.
No. And the remaining 10 are D's. Well, that doesn't leave remaining 10. That's 76.
Okay, so that's not it. Let's go to 1660.
Okay, hold on. Do we know which way we have to go? I mean, obviously we have to go higher, but we can tell from this answer that we have to go higher because these numbers are going to get subtracted from this number. It's not that obvious which direction, but let's go to 200 next, not 160.
Okay.
160 will not definitively answer it, notice. If 160 was too little, we might have to try D, and then of course we would know it was E. But by trying D next, we guarantee we know the answer immediately. So always on these back solving, think the second lowest and second highest.
Okay.
So let's do 200.
1/5 is 200. 40. 50. 100. And then 10. So we have 200. Sure does equal.
Bingo. And if 200 wasn't correct, we would have known it was either 160 or 400 because now we know which direction we're going. And we knew that because 80 gave us a number that didn't work in the same way that 200 would have given us. It wouldn't have worked in the same way. We would have known we needed higher, more, or lower.
All right. 176.
I like. I'm always amazed at how clever they can be on their questions.
2 times some number between 165 minus 5. Did it increase?
Okay, so 1 is correct.
What? I'm not entirely sure, but I think that would work. I mean, but what if you only increase by a point percent?
Well, here's the thing you want to see. That if we're going from 165 to 166, this quantity, 2 times that number, gets bigger.
Well, I know that, but if...
That's all you need to know. It doesn't matter whether we're subtracting 5 from it. we're going to be subtracting 5 from a bigger number. So if 2x gets bigger, then 2x minus 5 is going to get bigger. In fact, 2x minus 100 would get bigger.
I don't know. There's a circumstance where that may not get bigger, I think. What if it was a negative number or something?
Well, in this case, it's positive numbers.
So, okay. So they tell you it's either 165 or 166.
Well, it's increasing incrementally across that number line. So it's going 165 and a tenth, 165 and a quarter, 165. It's getting bigger.
Okay, you're
getting
right.
bigger. So this is getting bigger. And if this is getting bigger, all of number 1 is getting bigger. Notice that numbers 2 and 3 are more complicated.
Oh yeah, if it's in a numerator, that number is going to get much, much smaller. However, the smaller it gets, the more of 1 you're left with. So I would say it does increase.
Well, if I say 1 minus, here, it's easier to see if you actually draw it out. This number is bigger than this number, right?
Yeah.
Okay. So this number here is smaller than this number here. So it is increasing when we go from here to here.
So when it increases, it does increase.
Right. In other words, that's true. 1 minus 1 over x does increase as x increases.
Right.
Okay. Now the most complicated one of all is 1 over, so let's again do the 165 squared minus 165 and compare it with 166 squared minus 166. Which number is bigger, that or that? How can I tell without doing the math? What if we related it to 2 smaller numbers that we could do the math? In other words, if I related it to 3 squared minus 3 compared to 4 squared minus 4, which of those is bigger?
9 minus 3 is 6. 16.
So as we count up, that's always bigger than that. And I'm quite sure that 5 squared minus 5, 20. So from doing an example with small numbers where we can do the calculations easy, we get the answer that this is the bigger denominator.
Which means that the number as a whole is smaller.
Yes, so it's not increasing on 3. So it's 1 and 2 only.
Yeah, I see that.
Okay.
Hmm. 10 inches wide, 10 inches long.
We could go through a lot of geometry here, but there's a formula that's easier to memorize? What the heck? I'm a horrible artist, but that's our box. Okay, and it's 5 by 10 by 10. Any box has 3 dimensions, a width, a height, and a length. There is a formula that the diagonal that goes from there to there, what that measurement is, and it's very much like the Pythagorean theorem. That's why I'm giving it to you, is because it's pretty easy to remember. If I said it's like the Pythagorean theorem, what is that distance, do you suppose?
It's the hypotenuse.
Well, kinda. It's not really a hypotenuse, and I don't think you want to get into looking at all the different planes and figuring out diagonals, because this one formula will tell you the answer almost instantly. It's the square. If I said it's like the Pythagorean theorem, then it's like the square root of 5 squared plus 10 squared plus 10 squared. That's the answer. Let's simplify this.
Why'd you put it all under the
radical sign? Because in a right triangle with A, B, and C, C is equal to the square root of A squared plus B squared. So all we've done is added a third dimension, and the only thing that does is add another square root under the square root sign.
Cool, I can remember that.
Yeah, cool. That's why I said it, because the other method of solving this, you would have to figure out this side and then figure out a different triangle to figure out that length. And it's just easier to remember this. So let's reduce this. What is this equal to?
So 225 is in square root. And I'm guessing that's 15 maybe?
Uh-huh. And I noticed that they like problems like this. You're liable to see a diagonal of a box kind of problem.
Okay.
And that is the greatest possible distance. You could, if you were to put a tape measure in there and you wanted to measure the greatest possible distance, it would be from one corner to the opposite diagonal corner.
Now, when they give me a three-dimensional shape like this, you're going to say, okay, find the furthest diagonal point in the box or whatever. And I know immediately, you know, Dave told me a good trick, use the Pythagorean-like equation where it's all under the square root. And
Right.
It's just that simple.
Let me give you another question. Here's a cube.
Okay.
It's 3 by 3 by 3. What's the distance from one diagonal to the opposite vertex? In other words, the greatest measurement you could fit in that box would be that thing right there.
Well, if I use that method you just showed me, I'm going to say 9 times 3 is 27, all into the radical. So radical 27.
That can be reduced. You're never going to see that as an answer, as one of your answers. All the answers will always be fully simplified.
So that would be 3 radical 3.
Right. And that'd be the distance of that thing.
Nice. Okay.
So if you had a fishing rod that was a millimeter less than that, you could fit it in there.
All right.
Should we go to data sufficiencies?
Yeah, let's do it.
Let's bring on the torture. 177.
Dave, we have another session tomorrow for an hour, right?
Yeah.
It starts at what time do we have it for tomorrow?
Oh, actually we don't have anything tomorrow on Sunday.
I didn't mean tomorrow. I meant Monday. I'm sorry.
Monday we've got it at 8.
Oh, we don't have anything tomorrow?
No.
Do you think you'll have time to dig out some of those harder questions that I've been having issues with tonight, or?
Well, yeah, or tomorrow, certainly. I got most of tomorrow off, and it looks like I'm going to be semi-snowed in. So, yeah, it's what I'll do is just go through the remaining questions, and any that I see that apply to any of these 5 points, I'll check mark, and we can focus directly on it. Although, let's see, we've got 2 hours more. That'll get us, we're going to get through to the end. So as far as this book goes, we're not going to have that many extra questions to look at, if you know what I'm saying. We're on, what, 170 already, and there's only 230 of problem solving. There's still probably another 100 data sufficiencies that we haven't looked at. But
Okay.
okay.
So, do you think we should spend more time on data sufficiency, or?
Your choice. I used to use a 3-to-1 ratio with time because that's the ratio of problem solving to data sufficiency on the test. You're going to have 3 times as many problem solving as you're going to have data sufficiencies. So I always used to, with Eric, I'd spend 45 minutes on problem solving, 15 on data sufficiencies, 1/4 of our time. But it really kind of depends on how strong you feel in the 2 relative areas. If you need equal work on both, then we should spend maybe another half hour on problem solving before we go to data sufficiency.
All right. Well, that's all right. We'll just.
What would you rather do?
I was just thinking to add another hour tomorrow morning
Okay.
with some of those problem solving problems I've been having.
Now,
Do you have any other sources though?
I've got lots of time next week.
Yeah, but that test is on Wednesday.
It's on when?
Wednesday.
Okay. You want to try to schedule a trip up here between now and Wednesday?
Do you think that'd be smart? Be a good thing.
Well, it gives us a chance to do that MBA test online. That's about the only way we can do that.
Well, I could do it tomorrow. I could make the trip tomorrow.
I think the roads will be clear. The snow's supposed to stop today, and we're not supposed to get that much. It looks like I got about 6 inches out here. So the trip should be doable tomorrow if you want to try that.
Okay.
You want to stop the session today and schedule a 2-hour one tomorrow? We could even schedule a little later in the day, give a chance for the roads to clear.
You know what? That sounds pretty good, actually. Do a 2-hour session tomorrow, and I'll kind of show up around. I get out of church usually around noon. It takes me an hour and a half to get up there. How about 2 o'clock?
2 to 4?
Yeah.
Let's do that. I'm sure the roads will be passable by then. It's not supposed to warm up tomorrow, but it's supposed to warm up over the next couple of days. Okay, so that's at my house, and we're going to cut short today's 1 hour.
Yeah. Sure.
And then we'll still see you Monday night at 8. Okay.
Let me write this stuff down because I forget. And now we added another hour.
Yeah, basically 1 more hour to that. So it's 14 times 28.
So I had 364 that I owed you, so that's another 28. Not ready.
392.
Let me see here. All right, so now it's 392.
Mm-hmm.
Okay, we'll do the MBA test tomorrow. And that's from 2 to 4.
Yeah, and this gives me enough time that I can look through and see if I can find any more. Although we have already, of the 5 things you told me, We've done a standard deviation problem. We've done a good sequence problem. We've done a pretty good inequality, a couple of those. We've done a good probability one, and we had a couple of Venn diagrams the other day. So
It's just that I haven't been able to solve them on my own yet. I've needed
okay.
a good amount of explanation. So maybe when we do the GMAT test tomorrow, you'll help me get through the sticking points, and I'll try to solve it as mostly myself as best I can.
Okay. And then I can also look through the rest of my problems that I have online and check mark the ones that apply to these 5 principles.
Please, yeah, thank you, Dave.
Okay.
And Monday's 8 p.m. and that's it for today. Okay.
Yeah.
392, 2 hours tomorrow, 8 o'clock on Monday. Thank you, Dave.
Sounds good. See you tomorrow, Stephen.
All right, bye.
Bye-bye.